Voilà, c'est bon.
Ah, c'était rapide. On commence? Je te présente.
Je vais peut-être mettre une petite lumière, cette fois que je suis dans l'ombre. Je ne sais pas si ça va changer grand-chose, mais on verra bien. Ouais, ça ne change pas grand-chose, c'est pas grave.
Non, mais ça va. Je vais passer en anglais. Allora, buongiorno a tutti, direi di cominciare perché... Ah, c'è ancora qualcuno che è arrivato. Direi di cominciare comunque, sono le 3:07. Comincio col presentarvi la speaker. So, let me introduce Béatrice Grenier. Béatrice Grenier is assistant professor in Grenoble at the University of Grenoble in France. And she's affiliated also with the COA, which is the Atomic Energy Commission of France, as you might know. But she works mainly in a third institute, which is the Institut Laurent-Langevin, which is the world leading neutron facility. It is the world leading experimental installation for research with neutrons, using neutrons to explore matter. And at the ILL, this institute is called ILL. Many things are studied, but one particular thing that is studied is magnetism. And Béatrice is an expert in magnetism. And she's always studied during her career quantum magnetism and quantum magnetism in crystals. And she studies both the structure with neutrons and the dynamics of the spins in different materials. She's been dealing with a host of different categories of materials. And today she will give us an overview of the latest results that she's contributed, with a nice introduction which has got didactic scope, most of all. So I hope that will be a talk that will be affordable, let's say, to also non-experts, but with some glimpse of last results for experts. I thank you again, Béatrice, for accepting this to give this seminar, and I pass to her the microphone.
Thank you very much, Andrea. Buongiorno a tutti. So, yes, I wish to thank you, Andrea, for having invited me to give this seminar. And as you said, I'm trying, okay, I had to arrange things with Zoom. So you should see my screen now, my presentation.
Yes, it's fine, it's visible.
Okay, so I will try to be, as you said, as pedagogical as I can. Please don't hesitate to interrupt me if you have any question. And okay, so maybe I can start. Okay, so today I will speak, as Andrea nicely introduced, about neutrons for magnetism, and I will focus in a study that my collaborators and I did in the spin chain compound. So I will start with a long introduction and ready to give you the insight to, I hope, follow the second part of the talk, which will be about our results in this compound, barium, cobalt 2, vanadium 2, oxygen 8, that I will simply call Bakovo from now on. Okay, so let me start with the thermal phase transition with the water phase diagram that I'm sure everyone knows. So as you know, a phase transition occurs between two different phases upon cooling or warming when talking about a thermal phase transition. And at the transition, there are thermal fluctuations. So if we take the example of the liquid water to the ice phase transition, so in water, so this is just a snapshot, as you know, it moves constantly in time. And while in ice, you have a long range ordering of your water molecules, and of course it is static. And so when water is cooled down to ice, you have a spontaneous symmetry breaking. And so both the translation and the rotation symmetries are broken. And the order parameter to describe this phase transition is the density. Now, similar to that, let me switch to a typical magnetic phase transition, which is the paramagnetic to ferromagnetic phase transition. So similarly, at high temperature, you will have some disorder like we had in water. It means that you will have all possible orientations for your magnetic moment. So we talk about a paramagnetic disorder. So you have fluctuating magnetic moments. It means that the total magnetization will be 0. But if you cool down, then you will have an ordering because the exchange interactions in your compound will take over the, sorry, there's a mistake, will dominate over the thermal fluctuations I should have written. Sorry for that. So it means that now, because you have some interactions between your magnetic moments, between your spins, they can order. And so if you have a ferromagnetic interaction, they will all align parallel to each other. And you can see easily that if you sum up all these magnetic moments, you now have a non-zero total magnetization. In that case, the order parameter is specifically the total magnetization that is plotted here as a function of the temperature. And in that case, the spontaneous symmetry breaking is the rotation symmetry. Now you can induce such a ferromagnetic to paramagnetic transition, not by varying the temperature, but now by varying some other parameter. For example, varying an external parameter at 0 temperature, or at least at very low temperature, then we talk about a quantum phase transition. By opposition with the thermal transition, which is a classical phase transition. And in that case, you can encounter many new and exciting phenomena. So here you have the typical phase diagram, temperature, pressure, where you will have an ordered state in this part. Let me put again this pointer, an ordered state at low pressure. And when you apply pressure, you end up with a disordered state. In the case of the ferromagnetic paramagnetic pressure, you will have the following, with a ferromagnetic order at low pressure, and above your quantum phase transition, you will go back to the paramagnetic state as you had at high temperature. The quantum one-dimensional antiferromagnets, which will be the topic of my talk, is really a playground to study quantum phase transitions. There are many examples. Of course, I won't comment on them, but just to give you a few examples of such situations. And I wish to stress that such transition can be sometimes also characterized or triggered by topological defects or excitations. Let me mention an example that maybe some of you know, because there was a Nobel Prize for that quite recently, is the Berezinski-Kostolich-Soles transition, where you have bound vortex, anti-vortex pairs below the critical temperature. And these objects are topological objects, which is a subject that is widely studied in the last years. Okay, so now let's go a bit more into detail for magnetic systems. My aim is really to give you the necessary basics, let's say, to follow the study that I will present on Bakovo. So typically, when you want to describe a magnetic system, we are used to write the Hamiltonian. The Hamiltonian is simply the energy of the system. So you will have the spins, so spin at site I and spins at site J, that are coupled through this exchange Jij. And of course, you will sum up on all of them. The aim, what phase will be stabilized? The phase that will lower this energy. That means that if J is positive, which is the convention I will be using for antiferromagnets, then you see that the two spins want to be antiparallel. So this is what we call an antiferromagnet. But on the reverse, if you take a negative J, you see that to minimize this energy, you must have parallel spins. And this is the case of the ferromagnet that I described a bit earlier. Another very important concept, well, another important ingredient when studying magnetic system is the magnetic anisotropy, which will in fact tell how will be the dimensionality of the spin. In the Heisenberg case, which means it can be any direction in the sample, it will cost the same energy. It means that the couplings for the spin components along X, Y, and Z will be the same. In some cases, you will have a planar anisotropy. We call that the XY model. And in that case, your spin will be forced to lie in a plane. Saying it differently, the coupling JZ between the Z components will be null. The third situation is the uniaxial one, the 1D situation, which is called the Ising case, where the spin are forced to lie in a single direction. In other words, you have only GZ that is non-zero. And Bakovo precisely will combine these two situations, as we will see later. It's an antiferromagnet with the Ising anisotropy. So now let's compare what happens in a three-dimensional Heisenberg ferromagnet and antiferromagnet. So Heisenberg, remember, it means isotropic. And what I mean by three-dimensional is that the exchange couplings are comparable in the three directions of space. So in that case, the Hamiltonian is written that way, as already seen. And let's take the simple example of a cubic system. Let's compare the situation between a ferromagnet and an antiferromagnet. So for ferromagnetic exchange, then you will have a three-dimensional ordering below some critical temperature that is called the Curie temperature. So all the spins, as said before, will be parallel. In the antiferromagnetic case, then we call the critical temperature the Néel temperature. And below this temperature, you will have this antiferromagnetic ordering, up, down, up, down. Now, to these orderings, you will have some magnetic excitations, that will be associated to each of these orders. What are they? These magnetic excitations are called spin waves or magnons, and they correspond to a precession of the spin around its equilibrium position. You see that it corresponds to transverse excitation. I mean that the fluctuations of the spin occur in a plane that is perpendicular to the direction along which the spins are ordered. Okay? So in the ferromagnetic case, the spin waves will look like this. Of course, keep in mind that all this is moving in time. Okay? This is just a snapshot. It constantly moves in time. So it will describe a wave with all the spins precessing coherently with one another. And the dispersion curve will look like that way. So the dispersion curve is the energy as a function of the wave vector in reciprocal case. It will look like this. In particular, you can notice that at this point, when Q is 2 pi over A, you have a zero energy. This position corresponds to the periodicity in reciprocal space, which means a periodicity of A in direct space. And you can easily understand that in the Heisenberg case, this excitation with this periodicity will indeed cost a zero energy, since all the spins are shifted the same. And we said there is no privileged direction because it's isotropic. So you see that they are all parallel, it costs zero energy. But of course, as soon as you move from this wavelength, it will cost some energy to initiate such an excitation. Now, for the antiferromagnetic case, you will have something similar, but now it will precess around the one up, down ordering. And now the dispersion relation will look like that. you can notice a half periodicity in reciprocal space, which is completely, well, which is easy to understand because now you have a doubling of the periodicity in direct space because it's now up, down, up, down. And here again, you can easily understand that here at this position, you have a zero energy because all spins are anti-parallel. And again, I'm in the isotropic case. So how can we determine the magnetic ordering and the spin excitations in a compound, as I will show you, thanks to neutron scattering? Do you have any questions on that, or was it clear enough? Okay, great. So let me continue. So now the neutron. I will try to show you that neutron is really a powerful probe for condensed matter, and particularly for magnetism. So the neutron is a subatomic particle. It was discovered in 1932 by James Chadwick, and the first neutron diffraction experiments dates from 1946. So the neutron has a mass of the order of 1 unit atomic mass. It has no charge and a spin half. What are the consequences of that? No charge implies that the neutrons won't interact with the electronic clouds and they will penetrate deeply in matter, and thus they will interact with the nuclei. We call this interaction a nuclear interaction. I will comment further in a while. They have a spin. That means that neutrons will interact also with the magnetic moments, that is with the unpaired electrons in the electronic shells, and also they can be polarized. So for this interaction with the magnetic moments is called the magnetic interaction. I will also give more details very soon. Another property that is extremely important is the particle-wave duality. Neutrons can be seen both as classical particles and as waves of wave vector k. This allows to write these formulas. So this one for the energy as a function of the wave vector k, where k is simply connected to the wavelength. And we end up putting the values in that. So m is the mass of the neutron, of course. We end up with this formula that tells you that for the wavelength in angstrom and the energy in milli-electron volts, this product with the square root of the energy is about 9. We'll see in 2 slides the consequence of this formula. Before that, I'd like to give you more details about nuclear and magnetic interaction. So first, nuclear scattering. First thing is that it's isotropic. So that's the first important thing. Second, the amplitude for nuclear scattering is erratic in Z, the number of electrons, and N, the number of neutrons in the nucleus of your atom. So on this small figure, you see for a few atoms, the comparison between the amplitude of scattering for X-rays and that for neutrons. For X-rays, as you may know, X-rays interact with all the electronic clouds, so the amplitude is proportional to Z, the number of electrons. But for neutrons, it's erratic. And for example, you see that for hydrogen, neutrons are strongly scattered, while for hydrogen, they are very, very weakly scattered. A third important characteristic of nuclear scattering is the Q dependence. Because the nucleus is very small as compared to the neutron wavelength, then the scattered amplitude by neutrons will be completely flat as a function of Q, where Q is the scattering vector in reciprocal space. While for X-rays, because the electronic cloud is quite large, this scattering amplitude will decrease when Q increases. Now let's move to the magnetic scattering for neutron. The first thing that is extremely important, I will need you to remember that for the last part of my talk, is that the magnetic scattering is anisotropic. Neutrons will see only the projection in the plane perpendicular to the scattering vector of the magnetic moments. So imagine that you interact with this magnetic moment and that the scattering vector is vertical. All you will see is the projection in this plane here. Okay? Another interesting thing is that magnetic scattering for neutrons has the same order of magnitude as for nuclear, which is not the case for X-rays, for those of you who know. Last, because now we are talking about an interaction of the neutron spins with the unpaired electrons, it's quite sizable in a direct space. So when you Fourier transform this magnetic density, you will see that you have something that will decrease very fast when Q increases. Okay, so remember that nuclear scattering is flat in Q, while magnetic scattering decreases very fast. Okay, so let me comment now on this formula that I discussed a bit later. In neutron reactors for research, we produce neutrons that have an energy of a few milli-electron volts, typically in this range. If you apply this formula, it means that the wavelength will be in the angstrom range, which corresponds precisely to the molecular size and interatomic distances in condensed matter. And this is the reason why you will be able to do diffraction, because they both have the same order of magnitude. So you will do elastic scattering and be able to study structure. Concerning the energy, they correspond precisely to the excitation energies in condensed matter. So neutrons are very convenient to study excitations because their change of energy when studying an excitation will be a small fraction of their incident energy, so you will have a good precision. What will neutron measure? They will measure what we call the partial differential cross-section. So don't worry with the details in this formula. I just wish to express that the neutrons will measure the double Fourier transform in space and in time of the correlation function. What's the correlation function? It tells you how an atom or a spin is correlated with all other atoms. How an atom or a spin located at position rj and time 0 is correlated with all other atoms at positions rj prime and time t. Then we call that pair correlation. But neutrons are also able to measure the self-correlation function, that is, how an atom or a spin is correlated with itself at a different position and different time. So I don't have the time to tell more about that, but just for those of you who heard about it, to access the pair correlation, you will do coherent neutron scattering, while for the self-correlation, you will do incoherent scattering. Okay, so let's see what information neutron diffraction will bring for the various states of matter. They allow to study crystals, liquid, and gases. And so what will you have? If you measure a crystal, you have a long range ordering in your material. So if you do if you do neutron diffraction, then you will see some Bragg peaks. The analogous of that for magnetic states will be a magnetic ordering. And in the same way, you will have some Bragg peaks that will be of magnetic origin. So you expect in a magnetic crystal, in a magnetic ordered crystal, to have Bragg peaks of both nuclear and magnetic origin. If now you have a liquid, then now you have a slow motion of your atoms. So everything will be broader and you will have only a short range ordering. And so the neutron intensity as a function of Q will look like that. The analogous for magnetic systems are what we call spin liquids. If now you have a gas, you have a complete disorder. So you have no correlation at all between your atoms, so that you will have something completely flat as a function of Q. The analogous for that in magnetism is the paramagnet that I described earlier. So let's focus on a crystal and let's see what are the associated atomic excitations, the phonons. So to measure phonons, we will be using inelastic neutron scattering, and you will measure some relation dispersion, so the energy as a function of Q, the wave vector. You can have two types of phonons, the transverse ones, where the excitations are perpendicular to the direction of propagation of your phonon's wave, or longitudinal ones. So if you want, a good advantage with neutrons is that the intensity for phonons is proportional to this term, which means that you can select whether you want to measure transverse or longitudinal phonons. If you want to measure transverse phonon, you will simply choose the scattering vector more or less perpendicular to the wave vector, while for longitudinal phonons, you will simply choose Q, well, big Q, parallel to small q. And here is an example of an energy scan. So you have a Q scan at a constant energy, where you have the neutron intensity as a function of h. So you are along this direction, so A star plus B star. So you see that is the example of a longitudinal phonon, where you nicely see the phonon on each side of the zone center. Okay, but as I told you, neutrons are very powerful for magnetism. So of course, I won't take the time to comment all this. My purpose was just to show you that you can study many, many different aspects in magnetism with neutrons. And for our concern, we will focus on the study of magnetic structures and magnetic excitations. Okay, so let me show you a historical example, the first results on magnetic neutron scattering that were done on manganese oxide. So first diffraction, and on my next slide, I will talk about the magnetic excitation. So when you do powder diffraction, the typical instrument will be a powder diffractometer, where you come with a monochromatic beam on your powder sample, and you will have simply some Debye-Scherrer cones each time you are in Bragg condition. And on your detector, you will simply measure the Bragg peaks. And of course, as I said before, these Bragg peaks can be both of nuclear and magnetic origin. So this is the example of such an instrument at Institut Laoé-Langevin in Grenoble, where you have here the multi-detector, and here your sample is placed in a cryostat. So this is the powder diffractometer that was measured in 49 by Clifford Schul, and this is what he obtained at ambient temperature, where you have no magnetic ordering. So these are nuclear Bragg peaks. When you cool down, you see some additional peaks that appear, and these peaks are of magnetic ordering, of magnetic origin. And you can, from their position, this is the Bragg angle here along X, from their position, you can determine what we call the propagation vector. And this vector will tell you what is the periodicity of your magnetic structure. This propagation is 1/2, 1/2, 1/2, which means that you have a doubling of the periodicity in direct space along A, B, and C. So this is an antiferromagnet. Then from the intensities, you can then refine the structure and also determine the amplitude and the direction of the magnetic moments. And this is what was obtained. Okay, where you see indeed that the periodicity is double because you have this up, down order. This experiment was the first confirmation of the antiferromagnetic ordering that was predicted some years before by Louis Néel. Some years later, another team did some inelastic neutron scattering on a triple axis spectrometer, which is the first instrument that was designed to do inelastic scattering. So let me briefly tell you how this instrument works before showing you the results on manganese oxide. So here you have your neutrons that arrive on a monochromator here and here. You select an incident wavelength, an incident energy. Then your neutrons are scattered on the sample here and here. they are scattered with different energies because they gave some energy to the system to produce these excitations. And then using another crystal, an analyzer, you will select the final energy that you want to detect. Okay? So the analyzer and detector are here. And so with such an instrument, you will be able to select both the scattering vector and the energy transfer that you want to measure. So in practice, with this instrument, you will be able to obtain in single crystals, but also in powder. But in single crystal, you will have the energy as a function of Q in some given direction. So the dispersion relation. And practically what you will do is either some constant energy scans, some Q scans at a constant energy, or some energy scans at a constant Q. And so you will cut like this dispersion curve and be able to determine the various points on this curve. And here again, you can measure both nuclear and magnetic excitations. So this is the technique that was used in '72 to determine the magnetic excitations in manganese oxide. And this is what they found along 3 different directions in the reciprocal space. And so from the amplitude of dispersion, typically you will be able to determine the exchange couplings between your spins. This is what they found. And you see here that you have a small gap. If you remember well, in the beginning of my introduction, we said that a simple antiferromagnet had no gap. Here you have a small gap. This is a typical signature of the existence of some small anisotropy in the system. Okay, do you have any questions on that before I move further with this long introduction? And I hope didactic, as Andrea said. Okay, so let me summarize what we saw up to now. We saw that in the 3-dimensional Heisenberg antiferromagnetic case, we have a magnetic ordering below the Néel temperature, plotted here, and the associated excitations are these magnons, where I plot again the dispersion curve. Now, let me go more into the topic of my seminar, which are what we call 1-dimensional Heisenberg antiferromagnets. What do I mean by 1-dimensional antiferromagnets? I mean that now you will have a strong coupling along one direction of space, but no coupling at all along the 2 others. So in fact, you have spin chains. And as I will show you, the physics is completely different as the 3-dimensional case. Something that is really exciting is the fact that whether you have half-integer spins, 1/2, 3/2, and so on, or integer spins, you have completely different properties. First, for the spin excitations, in the first case, you have no energy gap, while in the second case, you have a finite energy gap. Second, in fact, you will have no ordering at one direction. But you will have some spin-spin correlation when the temperature goes to 0. And you see that it will be completely different in both cases. This spin-spin correlation will decrease much faster in the integer spin case. The first type of system is what we call a Tomonaga-Luttinger liquid. And the second case is what we call a spin liquid. So in the first case, these are typical excitation spectra that were measured in 2 such compounds with spin 1/2. And interestingly, you see a non-gapped dispersion here, but above that, you have all a part with a continuum of excitations. I will comment further on that because this is something really fascinating and interesting to explain. While in the integer spins case, as I said, you have a gap in energy, which is nicely seen in this measurement. Again, it's the dispersion curve. You see the gap. And here you have no continuum above. Let me come back to this continuum of excitation and let me explain you by hand what this corresponds to. So in fact, these are no longer, these excitations that you see here are no longer magnons as we measure, as we see in three-dimensional antiferromagnets, but they are what we call spinons. What are spinons? In fact, they are domain walls. Imagine an Ising chain with these antiferromagnetic correlations. Let's say it's the Ising case with all spins up or down to make it simpler. You will send your neutron beam, it will flip a spin. You see that if you flip a spin, you create two domain walls. These are my two spinons. Because you have no coupling at all between one chain and the next one, you can easily understand that these two domain walls can propagate along your chain with no energy cost. And so this is why you will have no gap. And this is also why you will have all this continuum of excitations, because your two spinons can be at many possible distances. So we talk about deconfined spinons in the sense that they can move individually with no problem. So why study such systems? As I just showed, you will see some new states of matter that are not encountered at higher dimension. We saw these examples of spin liquid and spinons. Second, you will be able to do exact calculations, which is very interesting to compare with some models. Third, you expect very strong magnetic field effects. Then you also expect a crucial role by frustration and isotropy and so forth. And last thing, which is very important, in reality, you do not have pure 1D system because you always have a very weak interchain coupling. So that's why we talk more about quasi 1D system, which means that you do have interactions along the two other directions, but they are much lower. And so Bakovo, which I will now present, corresponds exactly to that case where you have an antiferromagnet with some Ising anisotropy. You have some small interchain interactions, so it's quasi 1D. And as I will show you, there are some strong magnetic field effects. So let's see now what order establishes in this compound, what will be the associated excitations, how will they be modified by these ingredients, and what will be the magnetic field effects. So before that, let me now write the Hamiltonian. Remember, we saw the Hamiltonian in the Heisenberg case. Now I'm writing the Hamiltonian in this anisotropic case, where the writing is a bit more difficult because now you will have a different exchange interaction between the Z component of the Z components of the spins and the X and Y components. So I will write the Hamiltonian like that. J is positive, so it's antiferromagnetic. And we call this model the XXZ because you have a different coupling along Z. And in the Ising-like case, remember that this anisotropy parameter is larger than 1, saying that the coupling between the Z components is larger than that along X and Y. In other words, the spins will prefer to align along Z because this coupling is larger. So the Heisenberg case is well known. I talked a lot about it in my introduction, but the Ising-like case is not so much known. It's quite well known on the theoretical point of view, but there were very few experimental studies, this is what motivated us to study the compound, and also because it's a very weakly Ising compound with delta only 2. So this interaction is only twice as large as those between those components. Do you have any questions before I now move to the... Okay, so in Bakovo, you have copper 2+ ion. So let me briefly recall that when you apply the Pauli laws and so forth, the spins in the last D shell, in the 3D shell, will be like that. So you have a spin 3½ and an orbital moment of 3. In Bakovo, you have some edge sharing octahedra, And it turns out from the crystallographic structure that is well known that you have some compression along the c-axis, and it is precisely this compression that is responsible for this Ising-like anisotropy. And so as a result, the c-axis, because this direction is the c-axis of the crystal, will be the easy axis for this compound. On top of that, you have some spin-orbit coupling. And so because of that, in fact, you will be able to describe this system by effective spins 1/2. In other words, you can neglect the excited state because they are much, much higher in energy. And so you can think only on the ground state, which is a doublet. And so it's you can think in terms of effective spins 1/2. So let me present you the crystallographic structure of this system. So here from the side, you see the spin chains, which are helicoidal chains that turn like this. And if you look from the side, you see here the chains from the top. So two of them are rotating that way, and the two others rotating like that when moving along the c-axis. The copper atoms are at the center of this oxygen octahedron. Okay. So as I already said, Bakovo is described by this Ising-like model. So I write again the Hamiltonian. And so you have a very strong interchain interaction. So in the chain between two successive cobalt of the chains, and you have a weak interchain interaction, J prime. And the most important one between all the exchanges that you have is that one that is plotted on this figure. So the first thing we did some time ago now, so I will directly show you the results. We determined the magnetic ordering that establishes at low temperature, below 5 Kelvin, typically. So here is the crystallographic structure again, and let me show you what we obtained by doing a single crystal neutron diffraction. So here you see the chains from the side. And so this is the ordering that we found. So just to help you visualize the left drawing with the right picture, here in blue, these spins in blue are the spins that are in these blue chains. Okay, so you see that you have an up, down ordering. Okay, so it's indeed antiferromagnetic. And here in red, this is the chain that you see here. So here also you have an up, down ordering. Okay, I show again the magnetic ordering here with the plus minus signs. Okay, so we did a magnetic structure refinement, and that's the way we could determine this magnetic ordering. We could confirm that the spins do align along the Ising c-axis. Second, it's indeed an antiferromagnetic ordering. Third, we could refine the amplitude of the magnetic moments, about 2.3 μb. And fourth, this refinement shows us that we have an antiparallel coupling, an antiferromagnetic coupling between two chains here in the diagonal direction. Then we measured the magnetic excitations. Before showing you the results, I wish to remind you what we have in the Heisenberg case. Remember, I've shown you that we have this continuum of excitations for the deconfined spinons. This is what we obtain on the triple axis, IN12, that's ILL also, for Bakovo. First, you see two main differences. First, you have an opening of the energy gap. This is due, as explained earlier, to some anisotropy. In our case, it's the Ising-like anisotropy. Second, you see that you do not have a continuum anymore, but you have some discretized excitations. In fact, this discretization is due to the fact that it's not a purely 1D system, but quasi-1D. Let me explain. If you create such a two spinon excitations, because you have this weak interchain coupling, you see that having flipped these three spins will cost some energy with the next chain. because you remember they want to be anti-parallel. As a result, your two spin-ons won't be able to deconfine as much as they can because this costs some energy. And so this can be completely explained and modeled theoretically. I will show you in a minute. And with this model, you can explain this discretization. So to fully model our measurements, we started a collaboration with Thierry Gamarki in Geneva and his postdoc, was his former postdoc, Shintaro Takayoshi. And they did some infinite time evolving block decimation calculation using mean field approximation. And let me show you the result of their calculations. And you see that they do reproduce the energy gap as we measure and the discretization of the excitation. There is only a small disagreement here where we have an anti-crossing and they do have not. Since then, we had an explanation for that, but let me skip this. And so with their calculations, they could find the values for the various exchange couplings. They were also able to reproduce very nicely our energy scans. I show here an example. So that's the neutron intensity as a function of energy. And you see that you have a fairly good agreement. Okay, so just to finish on the zero field study. So all this, I forgot to mention, occurs with no external magnetic field. Now it's interesting to compare two energy scans. One at this wave vector, 002, and the other one at 301. When Q, so the scattering vector, is along C, 002. Q is parallel to M. You remember at the beginning of my talk, I said that neutrons are sensitive only to the fluctuations that are perpendicular to the magnetic moment. In other words, in this configuration, you will be able to measure only the magnetic excitations that are along A star and B star, so in this plane, which means that these excitations are perpendicular to the ordered moment, so they are transverse. In the second case, you see now that Q is oriented that way. So if you put a scattering vector along 301, you will be able to measure both transverse excitations along A and B and longitudinal excitations along C. And you see now that in addition of these series of transverse excitations, which are the same than on the left, you have an additional series of excitations. And so those are longitudinal because they were not present in the previous measurements. Okay? So to conclude on this detailed study, we were able, thanks to the anisotropy of the magnetic excitation of the magnetic interaction for neutrons, we were able to show that in Bakovo, you have two series of interlaced series excitations that we can call Zeeman ladders, some longitudinal and transverse ones. Do you have questions about that before I move to my last part? Okay, so let me move further. Now we were interested in applying a magnetic field in the B direction. Let me briefly tell you what were the motivations for this work. These are the field temperature phase diagrams that were obtained by macroscopic measurements, whether you apply the field along the A plus B direction or along the B direction. You can see that you also have some strong anisotropy in the AB plane. We are interested in the second case because you see that here you have a phase transition at about 10 Tesla. Such a field is accessible with neutron. And so our point was to characterize this phase transition and determine the nature of the phase above. So before showing the neutron results, I'd like to tell you about some theoretical work that was done from this phase diagram. Timourin and collaborator had a careful look on the structure, and it turns out that the c-axis is slightly turned from the easy axis of magnetization. I'm sorry, I need to éternuer, I don't know in English, to atchum. Okay, it's gone, sorry for that. So you have a small tilt of 5 degrees between the easy axis and the c-axis. And remember, you have such screw chains. And so this means that if you apply, so it's a work that was able to show that if you apply a uniform field along the b-axis, in that direction shown here, it will induce a staggered field along A. So again, the appearance of this staggered field due to the uniform field is a direct consequence of this tilt by 5 degrees. While if you apply the magnetic field along A plus B, you don't have the appearance of such a staggered field. And this is the reason that explains the big difference between these two curves. So here in blue, you will end up with saturation that is, so when all your moments are parallel at about 40 Tesla, while if H is along B, you have to wait for a much larger field to reach saturation. Okay, so now let me show you the magnetic ordering that we obtained thanks to single crystal neutron diffraction, so still on D23 at ILL. So here, just for a refresher, let me plot again the magnetic structure in zero field. You remember we had these chains here with the spins parallel to C, up, down, up, down. If now you apply a field, so here you have a top view from the chains, so C is like that. And at the bottom, you have a view from the side of the chains, and B is pointing towards you. If you applied a magnetic field along B, you see that the spins progressively rotate, and above the critical field of 10 Tesla, now you still have an antiferromagnetic ordering, but now the spins are along the A direction that is parallel to the staggered field that appears when you apply the uniform field. So it's still antiferromagnetic, but now the spins are not along the easy axis, but they are along this staggered field. Another difference between these two structures is that here you had an anti-parallel coupling, you remember, while here you have a parallel coupling. So a different propagation vector. So what we decided to do then is to do a field dependence of the amplitude of the magnetic moment along C, this one, and the same, but for the amplitude of the magnetic moment along A as a function of the field. This is what I will show now. So along C, we find the typical behavior for another parameter. So you see that the magnetization decreases like this and vanishes at the critical field. While along A, interestingly, you see that we have an unusual behavior since the magnetic moment along A increases progressively as soon as you start applying the uniform magnetic field. And this again confirms that this is due to this staggered field itself induced by the uniform field. Just to mention that again, the calculations, the theoretical calculations are in quite good agreement with our data. So this study shows that we have a competition between the easy axis anisotropy and this staggered field. So this transition, this quantum phase transition is really unconventional and makes it very interesting. Let me now talk about the excitations, and then I will nearly come to the end. So what we studied then is we went at a Bragg position where you remember we have these discretized excitations. And we followed the minimum of these dispersion curves as a function of the field. And so let's focus on the lowest excitation, this one. You see that when you apply the field, it splits in two branches. One goes down down to the transition and up again, and this one always goes up. To better understand the character of these excitations, we used polarized neutrons on IN12, triple axis at ILL. Let me explain in a simple way how this works. Polarized neutrons will allow you to separate the fluctuations that occur along the direction of the field. In that case, the spin of the neutron will stay the same after the interaction. So we call that a non-spin flip process. While the neutrons that will scatter that will make a magnetic excitations in a direction that is perpendicular to their spin will flip. And so in the spin flip channel, we will measure the spin fluctuations along A and C. And so this is what we did. So we did some energy scans with the two channels at these positions indicated here. And you see that the lowest branch here appears in the spin flip channel. It means that the neutron spin has flipped. So it has to be fluctuations perpendicular to the applied field. So perpendicular to B. While the branch here appears in the non-spin flip channel, so it has to be fluctuations of the spins along B, along the direction of the applied field. Now to go further, we wanted to know if the spin fluctuations for the lowest branch were along A or along C. So for that, we use again the fact that the magnetic interaction is anisotropic. Remember, neutrons can measure only the fluctuations perpendicular to the ordered spins. So it means that since well, maybe I should immediately show the results because I think I'm running out of time. Just let me state that using the anisotropy of the magnetic neutron scattering, we could show that the fluctuations at low field occur along the A direction, while in the high field phase, they occur in the C direction, because here we have no signal at all. So just to summarize on this result, and really doesn't matter if the previous slide was not very clear, sorry for that. What I like to say, which is important, is the following to conclude on this study. At zero field, we have the magnetic moments that are ordered along C, the easy axis, while for the lowest branch, the magnetic excitations are along A. So it's transverse. At 12 Tesla, remember that now the magnetic moments are ordered along A, along the staggered field, while the magnetic excitations are along C. So you see that again, it's transverse. And so when you go from 0 to 12 Tesla over the complete field range, our study shows that the lowest branch corresponds to transverse fluctuations. Okay, so to conclude, I hope that I've convinced you that neutrons are a privileged tool to study magnetic orderings and excitations. And second, I hope that I've been able to show you that this system exhibits very interesting magnetic properties. And just to come to a concept that I mentioned in my introduction to topological defects and excitation, I wish to say just a few more words about these two phases at 0 and 12 Tesla in Bakovo. In fact, this quantum phase transition results from the competition of two types of dual topological excitations. Yes, I forgot to mention that spin-ons are topological excitations. So at zero field, these topological excitations are the spin-ons that carry a spin half along C, and they are both transverse and longitudinal. While at 12 Tesla, you have a completely different topological object, which are the dual excitations of the spin-ons. Now they have spin 1, which means that they correspond to bounded spin-ons along A, and those are only transverse, as I have shown in the presentation. So with that, I would like to thank all my collaborators, and in particular, Virginie Simonet, Sylvain Petit, Thierry Giamarchi, and his postdoc Shintaro, and the two previous PhD students that have been working on this study. And of course, I thank you very much for your attention. And sorry, I think I was a bit too long. Thank you very much. We don't hear you, Andrea. Grazie mille. This is all the Italian I know.
Yes, my microphone is on now, I guess.
Sorry?
My microphone is on now.
Yeah, yeah, it's on. Yeah.
Thank you very much for the seminar and for this wide introduction about neutrons and magnetism, and then the specific focus on Bach-Orban.